Hello YouTube. Today we're going to examine Bayesian epistemology, which is one of the most popular theories of confirmation in modern philosophy of science. Now, the literature on Bayesianism is quite vast and often pretty technical, so we're going to focus on the fundamental philosophical concepts here rather than on the mathematical probability theory. I think many of the fundamental ideas of Bayesianism are reasonably straightforward, so we're going to try to unpack those in this video, but I do want to make it clear that if you're looking for an in-depth analysis of Bayesianism, you're not going to find it here. That would require a whole series. So first of all, let's state how confirmation works according to the Bayesian. So the only technical notion we need for this is conditional probability, which is the probability of A given B. The probability of A conditional on some other fact B. And so that's what this represents here, the probability of A given B. If I have a fair dice, I might ask, what is the probability that I roll a 3 given that I roll an odd number? Well, we know that that's 1/3, right? So we can write that like this, probability of 3 given odd. So similarly, we can talk about the probability of a hypothesis given a piece of evidence. What is the probability that John is at the beach given that it's sunny? Or what is the probability of general relativity given a particular value of light bending around the sun, or whatever? Now, to put it simply then, the basic Bayesian claim about confirmation is that some evidence E confirms a hypothesis H if and only if the probability of H given E is greater than the probability of H. And on the other hand, the E disconfirms H if and only if the probability of H given E is less than the probability of H. So to confirm a hypothesis then, the probability of the hypothesis after the evidence is acquired must be greater than the probability of the hypothesis before the evidence was acquired. And I should note that we say that the probability of H is the prior probability of H, and the probability of H given E is called the posterior probability of H. Okay then, let's turn to the details. Well, Bayesianism is constructed on mathematical probability theory, which can be summarized in these 3 axioms. So axiom 1, every probability is a number between 0 and 1. Axiom 2, if A is a necessary truth, then the probability of A equals 1. And axiom 3, if A and B are mutually exclusive, which is to say if it's impossible for both A and B to be true, then the probability of A or B equals the probability of A plus the probability of B. And from those very simple, straightforward axioms, you get the whole of probability theory. We can derive lots of results about probability from these axioms, and I mean, as a mathematical theory, this is totally uncontroversial. What makes Bayesianism a substantive epistemological position is its interpretation of the probabilities and its sort of use of this interpretation in a whole theory of rational belief. So Michael Strevens, in his notes on Bayesian confirmation theory, identifies 3 central tenets of Bayesianism. So the first tenet, well, we noted that one of the axioms of probability theory is that every probability is a number between 0 and 1. And one way in which probability theory is important for science, according to the Bayesian, is that these probabilities are interpreted to be degrees of belief, or sometimes called credences. So the number between 0 and 1 represents your degree of belief or your credence in the proposition. Basically, your confidence that the proposition is true. So if the probability of A equals 0, if you assign 0 to the probability of A, then you are certain that it's false. If you assign 1 to the probability of A, you're certain that it's true. If you assign 0.5, you're undecided. If you assign 0.9, you're very sure it's true, but maybe you could be wrong, and so on. So when we ask about the probability of a hypothesis, we are asking about your subjective degree of belief in the hypothesis. So there's a couple of things that are very important to note here. The first is that for the Bayesian, the probability of a hypothesis is a matter of psychology. It's a matter of a person's psychology. A probability doesn't state how probable something really objectively is. Right? It simply states your degree of belief in it, your judgment about it. That's all there is to probability. So the Bayesian interpretation of probability is known as subjective probability. Right? For the Bayesian, probabilities are degrees of belief. Right? They're not sort of facts in the world that people can be right or wrong about. There is no observer-independent fact of the matter about the probability of a proposition. A proposition is either true or false. And then the probability of a proposition is a person's degree of belief in its truth or falsity. So think of a coin toss. I say there's 0.5 probability that the coin will land heads. But I mean, that's the coin is either going to land heads or tails, right? And if I had access to more of the facts, or if I had like better cognitive capacities, then maybe I'd be able to predict with greater accuracy whether or not the coin would land heads. If I knew exactly the way the coin was flipped, or if I knew exactly what its surrounding environment was like, maybe I'd be able to predict exactly how it would land. So to say that there's a 50% chance of landing heads, 50% probability of landing heads, that's just an expression of my sort of subjective degree of belief given my epistemic position in the world. Now, another thing that follows from this first tenet is that when we speak of believing or disbelieving a theory, for the Bayesian, that's a simplification, right? Belief is not an all or nothing matter. When I say that I believe a proposition, I just mean that I assign it a probability above a certain threshold, so maybe above 0.8. But belief is really a spectrum of commitment. Evidence comes in and that alters your degree of belief. Some theories you'll have a higher degree of belief than others, and I think this is fair enough, right? I mean, I may believe that it will rain in Exeter tomorrow, but I might not be certain. I might say that I'm 80% or 90% sure that it will rain in Exeter tomorrow. I'm much more sure that the sun will rise tomorrow. So I'd maybe say that I'm like 99.9% sure of that. But even there, I'm not absolutely certain. So I think this is a fairly natural way of speaking about our beliefs. Almost all our beliefs about the world seem to work in this way, and the Bayesian would say it's the same with scientific hypotheses. We have different degrees of belief in them. Okay, so how then do we measure degrees of belief? Well, a standard procedure for the Bayesian is to measure degree of belief in terms of betting behaviour. The thought is that the higher your subjective probability for A, the lower the odds you would accept for betting on the truth of A. So suppose I tell you that you can pay to enter a bet where if A is true, you win £100. How much would you pay to enter? Well, if you assign a high probability to A, let's say 0.9, well, you're going to pay a fairly significant sum, right? You'd probably be willing to risk, say, paying £90. So if, let's say, you take the proposition the sun will rise tomorrow, I give you £100 if this proposition turns out to be true, and nothing if it turns out to be false. How much would you pay to enter that bet? Well, I mean, that's easy money. You probably would be willing to go all the way up to £99.99. On the other hand, if you assign a low probability to A, you'd need the winnings to be significantly greater than the amount you'll pay to enter. So you'll only pay, say, £10 to enter. So sorry, that should say just there. That should say if you assign a low probability to A. My mistake on the slide there. But yeah, if you assign a high probability to A, you'll be willing to pay a lot of money on the bet that A is true. If you assign a low probability to A, you'll be willing to pay much less. Now, of course, betting behaviour is going to depend on features of your personality, like how much of a risk taker you are, but Bayesians think that it offers a reasonable way of at least approximating a person's degree of belief. The more confident you are in the truth of a proposition, the lower the odds you'll accept for betting on its truth. I mean, in particular, I think that this this feature of betting behaviour is supposed to illustrate that belief really does come in degrees, right? You don't just have beliefs and then things you disbelieve and that's it, right? You really do have this kind of spectrum of commitment, and that spectrum of commitment is revealed in the way that people are kind of, they're willing to bet different amounts on different propositions. Okay, so the second tenet of Bayesianism is that if you are to be rational, The probabilities you assign to different propositions must conform to the axioms of the probability calculus, the 3 axioms that we mentioned at the beginning of this video. So your degrees of belief must conform to those axioms, obviously. Now, of course, people are not perfectly rational. Their degrees of belief don't actually conform to the probability calculus. So here the Bayesian is making a normative claim. Your degrees of belief ought to conform to these axioms. So this is what we might call a synchronic rationality condition. It gives the conditions that rational degrees of belief must satisfy at any given time. So, for example, if you assign a probability of 0.8 to A, you must assign 0.8 or lower to A and B, to the conjunction A and B, because A and B can't be true unless A is true. So if the probability of A is 0.8, the probability of A and B can't possibly be higher than 0.8. Similarly, if you assign 0.8 to A, you must assign 0.2 to not A. If you think that A is a logical truth, you must assign 1 to A, and so on. So the question then is, well, why? Right? Why must degrees of belief conform to the probability calculus? Well, here the Bayesian often appeals to what are known as Dutch book arguments. A Dutch book is a combination of bets that ensures a loss. So heads I win, tails you lose is a loss that ensures you will lose money. That's a bet that ensures you will lose money. So you definitely don't want to enter that bet. And the claim is that if your subjective probabilities violate the probability calculus, you will be committed to making bets that guarantee a loss. And assuming your goal is to increase your wealth, it would be irrational to enter into a bet that guarantees a loss of money. So here's a simple example of how a Dutch book can be constructed against someone whose degrees of belief do not conform to the probability calculus. Suppose I take A to have a probability of 0.8 and I take not A to have a probability of 0.8. Well, then, if we're right about the link between degrees of belief and betting behaviour, well, in that case, I'd be willing to pay £80 to enter for the prize of £100 if A is true. I'd also be willing to pay £80 to enter for the prize of £100 if A is false. But obviously, if I make both bets, I will pay out £160 and I'll get £100 back. So a loss is guaranteed, no matter whether A turns out to be true or false. Now, it's been proven, and this is known as the Dutch book theorem, that no Dutch book can be made against somebody who obeys the probability calculus, and a Dutch book can always be made against somebody who fails to obey the probability calculus. So in other words, obeying the probability calculus is necessary and sufficient for avoiding Dutch books. We won't go into the proofs of that here. You can look it up if you want the technical details, but those proofs are there. Of course, the relevance of these proofs assumes that degrees of belief translate into betting behaviour in the way the Bayesian claims. I guess it's a pretty intuitive idea that if your degrees of belief don't conform to the probability calculus, then your beliefs are at least potentially self-defeating, right? You will have at least some motivation to make bets that will necessarily make you worse off. Okay, so that's the second tenet of Bayesianism. The third tenet of Bayesianism is Bayesian conditionalization. And this tells you how to update subjective probabilities, update degrees of belief based on the evidence. It tells you how your degrees of belief should change in response to new evidence. Now again, like the second tenet, this is a normative claim. The second tenet was a synchronic rationality condition, giving the conditions that rational degrees of belief must satisfy at any given time. This third tenet is a diachronic rationality condition. It gives the conditions that rational degrees of belief must satisfy over time. So, okay, what is Bayesian conditionalization? Well, the idea is that when you receive some piece of evidence E, right, you set the probability of H to be equal to the probability of H given E. So the probability of H given E becomes the probability of H, right? The new probability of H is the old probability of H given E. And I think this is fairly intuitive. So let's say I roll a dice and I don't tell you what number came up. What's the probability that I rolled a 6? Well, it's 0.16 recurring. But now I ask you to imagine, just just for fun, right? Just imagine that I rolled an even number. Well, assuming that I rolled an even number, right, what would be the probability of a 6, right? So what is the probability that I rolled a 6 given that I rolled an even number, right? The probability of 6 given even. Well, in that case, it's 0.3 recurring. Now, if I reveal to you that I did in fact roll an even number, well, now you'd say that the probability that I rolled a 6 is in fact 0.3 recurring. So the probability of rolling a 6 given that I rolled an even number becomes the probability of rolling a 6 when you learn that that I did in fact roll an even number. So in general, when you get evidence E, your new confidence in H is your old confidence in H given E. The slogan that's often used here is, today's posterior is tomorrow's prior. And over time, you update your degrees of belief by applying this rule. Now, notice that both the prior and the posterior can be determined before the evidence is acquired. So, you have both the prior and the posterior in advance, as it were. It's just that, before you've got the evidence E, you'll have many different posteriors corresponding to many different possible pieces of evidence. So when you eventually do get the evidence E in, you can just take that probability of H given E and then set the probability of H to be equal to that. So yeah, I think that's a fairly simple idea. But you might say, well, okay, beyond its intuitive appeal, why should we update our beliefs in this way? Here again, the Bayesian appeals to Dutch book arguments. If you were to use some other rule for updating your beliefs, it would be possible for a Dutch bookie to offer bets against you that would ensure a loss. So again, both of the Bayesian rationality conditions rest on these Dutch book theorems. Okay, now all of this brings us to an important question. How do we know whether the posterior probability is higher than the prior probability? And if it's higher, how do we determine how much higher it is? I mean, there's a difference obviously between going from 0.6 to 0.65 and 0.6 to 0.95. So how do we calculate this? And this brings us to the heart of Bayesian epistemology, Bayes' theorem. A theorem so this can be derived from the axioms of probability theory, and it tells us how to work out the posterior probability. And I've presented the simplest form of the equation just here. So the probability of H given E, the posterior probability, equals the probability of E given H multiplied by the prior probability over the probability of E. So I should just say as a terminological note that in the literature on Bayesianism, the probability of E given H is often called the likelihood of H on E. Now, that's somewhat confusing because, in regular talk, we often use the terms probability of the hypothesis and likelihood of the hypothesis interchangeably. But that's not the case in Bayesianism. Those words have quite different meanings. So, if you're ever reading about Bayesianism, just be wary of that term likelihood. Right, likelihood refers to the probability of E given H, so that the likelihood of H refers to the probability of E given H. So again, it's slightly confusing, but that's the terminology. So anyway, that's Bayes' theorem. I guess it's perhaps obscure just why this is so important. So let's apply this to a couple of examples. Suppose you are considering whether or not to hang the washing outside to dry. You're worried that it might rain later because you can see thick clouds. So you want to know, all right, what's the probability that it will rain later given that it's cloudy now, right? And so there's our two. So the hypothesis is it will rain later today. The evidence is it is cloudy this morning. Okay, so the probability that it's cloudy this morning given that it will rain later today. So this is the probability of E given H, probability of the evidence given the hypothesis. Let's say this is 0.6. So on 60% of the days when it rains, it's cloudy in the morning. The probability of rain, right? This is our prior probability that it will rain later today, the prior probability of the hypothesis. This might be, let's say, 0.2. because 20% of the days in this month are rainy. Finally, we have the probability of cloud, the probability of morning cloud. This is probability of E. Here in the UK, it tends to be cloudy fairly often, so let's say that's 0.4. 40% of days this month are cloudy. Now, if we plug these numbers into Bayes' theorem, we have it that the probability that it will rain, given that it's cloudy this morning, is 0.3. So the cloudy morning does confirm the hypothesis, but not very strongly. The prior probability, as we said, the prior probability of rain later, as we said, is 0.2, and the posterior probability is only 0.3. So it's probably not going to rain. At least, for something like hanging the washing outside, that's maybe an acceptable risk. Okay, let's apply this to a slightly more sophisticated example. Suppose that as part of a routine medical exam, I'm given a HIV test, which unfortunately comes back positive. Now, we'll assume that the test has a 1% false negative rate. So in other words, 1% of the people who do have HIV get a negative result. It also has a 2% false positive rate. So 2% of people who do not have HIV will get a positive result. And those percentages initially don't sound too good for me. It looks like a pretty good test. So, obviously I want to know, right, what's the probability that I have HIV given that the test was positive? And we've got it here in the Bayesian form. So our hypothesis is I have HIV. The evidence is the HIV test was positive. Okay, let's plug in the numbers. So for the probability of a positive result given that I have HIV, so this is the probability of E given H, well, we can immediately see that this is 0.99 because we said that the test has a 1% false negative rate. A 1% false negative rate means that if 100 people with HIV are given the test, 99 of them will test positive. So probability of positive result given HIV is 0.99. For the prior probability that I have HIV, well, we would look here at the prevalence of HIV in the population of people like me. So HIV isn't all that common in the UK, and I'm not in a high-risk group. I don't inject heroin and things like that. So let's say that only about 0.1% of people like me have HIV. So the prior probability of HIV is about 0.001. What about the prior probability of a positive result? Well, since we know the general prevalence of HIV, and we also know the false negative and the false positive rates of the test, we can calculate this. So 0.1% of people are HIV positive, and 99% of them get a positive result. On the other hand, 99.9% of people do not have HIV, but 2% of them get a positive result. So using this information, we can calculate the probability of a positive result, just the overall probability of a positive result, like so. And we find that the overall probability of a positive result is 0.02097. So plugging all of these numbers into Bayes' theorem, we find that the probability that I have HIV given a positive result is approximately 0.047. I probably have nothing to worry about. This posterior probability that I have HIV is higher than the prior probability, so the positive result does provide some confirmation to the hypothesis, but it's nothing to be concerned about. Now, this result may be a little surprising because, as we saw, it seemed like a fairly good test. And actually, a 1% false negative rate, 2% false positive rate, that is a pretty good test. But what we have to bear in mind is the base rate of HIV in the overall population. So I think it's tempting to make the inference here that a 2% false positive rate means that if I get a positive result, I have a 98% probability of having the disease. And this inference is known as the base rate fallacy because it neglects the base rate of the disease. HIV is actually fairly rare. The prior probability of contracting it is quite low. So if you were to give the test to everybody, the majority of positive results would be false positives. Right? The chances are that if you've got a positive result, you'd be one of the false positives. The intuitive way to think about this is that 2% of a huge group, so the 2% false positive rate, may be larger than 99% of a fairly small group, the 99% being the true positive rate. When people get tests for diseases, it's usually because there's some reason to think that they are at risk of the disease. Maybe they're showing, symptoms of the disease, or maybe they're just in a high-risk population for the disease. So they're in a specific population where the disease is more common. If you show other symptoms associated with HIV, or if you are a heroin user or something like that, these things may put you in a population where the base rate of HIV is, say, 30%. So the prior probability that you have HIV would be 0.3. And if you do the calculations with that figure, you'll see that the posterior probability, the probability that you have HIV given that you got a positive result, is very high. So in that case, the positive result would provide very strong confirmation to the hypothesis that you have HIV. So, I guess the point of all this is that Bayes' theorem is unquestionably useful in many contexts. And hopefully you've got some idea there of how the theorem works and how it can be applied. So let's just reiterate then I guess the kind of core claims of Bayesianism. So the fundamental idea of Bayesian epistemology is that E confirms H just in case the probability of H given E is greater than the probability of H. So the posterior probability is greater than the prior probability. Furthermore, we update our beliefs by Bayesian conditionalization. When we acquire evidence E, we set our new prior to be the old posterior. And we work out the posterior probability by applying Bayes' theorem. And since Bayes' theorem can be derived from the axioms of probability theory, well, as long as you accept the claim that probabilities are degrees of belief and that rationality requires conformity to the axioms of probability theory, then we get the whole Bayesian framework from those fairly simple ideas. A couple of points just worth noting here. First of all, the lower the prior probability of the evidence, the greater the degree of confirmation it provides to the hypothesis. Bayes' theorem tells us that the lower the value for the probability of E, the higher the value for the probability of H given E. And again, this is it's an intuitive idea, right? We have seen this already many times in this series, the suggestion that surprising novel predictions provide stronger confirmation than other types of predictions. So take something like gravitational time dilation. That was a surprising, unexpected prediction. We would have assigned it a low, we would have assigned a low probability to that before general relativity was proposed. And so when it turns out to be true, it provides strong confirmation to the theory. On the other hand, if a theory of gravity predicts that, stones will eventually fall after they've been thrown into the air, that's not surprising at all. So that would be a very high probability of that evidence, and so would provide very little confirmation. So the Bayesian can capture what's important about novel, surprising predictions. Okay, another thing to bear in mind here is that working out all of these probabilities obviously takes place against background knowledge. So we might give a maybe more precise or just different form of Bayes' theorem that explicitly puts the reliance on background knowledge into the theorem, which looks like this. For the rest of this video and the next, we'll just take the simpler form of the theorem. But bear in mind that you might prefer to use this form. I suppose it's maybe technically more accurate, let's say. Okay, so we've seen how Bayes' theorem works in some simple examples, but how do we apply this to sophisticated scientific theories? One of the big issues when it comes to thinking about scientific theories is how exactly we determine the probabilities that we plug into Bayes' theorem. So, probability of E given H. Well, obviously this depends on the relation between the hypothesis and the evidence, and in many cases this is, I guess, probably the most straightforward part of this. If the hypothesis deductively entails the evidence, then obviously the probability of E given H is 1. And similarly, if the hypothesis is a statistical hypothesis, it may specify the probability that E is true on H being true. It will specify the probability that the evidence will occur on the hypothesis being true. So to say that an atom has a half-life of 2 years means that the probability of some specific atom decaying in 2 years is 0.5. And from that you can easily work out the probability of decay in other periods of time. So the probability of the evidence, before it's acquired. Well, how do we work this out? Well, we saw in the HIV test case that we can work out the probability of E by looking at the probability of E given H and the probability of E given not H. Now this is easy enough in the HIV case because we had, I suppose, two very specific hypotheses. You have HIV or you don't. But how does this apply to scientific theories? What's the probability of gravitational time dilation, assuming that general relativity is false? The problem here is that there are a whole host of possible hypotheses that entail claims about gravitational time dilation, most of which we've never even thought of, and all of which would, say different things. So clearly we have no way of working out in this case, what the probability of E given not H is. And in fact, there may not be any fact of the matter what it is. Maybe one possible solution to this is just to take not H to refer not to all possible alternatives to H, but just to the serious rivals to H at any given time. So, you work out the probability of E by considering the probability of E given H, the probability of E given H1, the probability of E given H2, and maybe for a few others, or something like that. That might be one way to come to a reasonable view of the probability of E. So what about the prior probability of the hypothesis? We need to know this, obviously, in order to apply Bayes' theorem, and of course the fundamental claim about confirmation involves a comparison of the posterior probability and the prior probability. And this has proven to be one of the major problems for Bayesian epistemology. So even in the simple case, like working out the prior probability that I have HIV, we actually run into some pretty serious difficulties. So when I was presenting that example, I assumed that in order to determine the prior probability that I have HIV, I should examine HIV rates in the relevant population. But what is the relevant population? Should I take the prevalence of HIV in all humans? Should I take the prevalence of HIV in the UK? Should I take the prevalence of HIV in straight white males in the UK? Should I take the prevalence of HIV in philosophy PhD students, in men who run YouTube channels, in men with long hair, whatever, right? What is the relevant population that I have to look at in order to get the base rate of HIV? Obviously, there are any number of ways I could define the population. So already, even with this fairly straightforward case, there are problems. But prior probabilities become even more obscure when we start thinking about sophisticated theoretical hypotheses like general relativity or the multiverse or punctuated equilibrium. How do you even begin determining the prior probability that macroevolution exhibits a pattern of punctuated equilibrium? Right? I mean, where do you even start with that one? So at this point, there's a big division in Bayesianism between subjective Bayesians and objective Bayesians. Now, all Bayesians agree that prior probabilities must be in conformity with the probability laws. So this is just to affirm the second tenet of Bayesianism that we discussed above. If you assign a prior probability of 0.7 to H, and there is some other hypothesis, H1, which is inconsistent with H, then you must assign a prior probability of 0.3 or less to H1. So all Bayesians agree that assignments of priors must be logically consistent. But of course that does nothing to tell us what the prior probability of H should be, So, according to subjective Bayesianism, there are no constraints on prior probabilities beyond the probability laws. So it really doesn't matter what prior probabilities you assign, as long as they are logically consistent. So imagine that you are told to draw a ball from an urn containing both red and black balls, and you're given no other information about the urn. You don't know who made it, what it's for. You aren't told what the proportion of black balls to red balls is. Now, before you draw the ball, you're asked to estimate the probability that the ball will be black. This is your prior probability, right? Your prior probability that the ball you draw will be black. Now, for the subjective Bayesian, it's rational to assign any probability whatsoever to this, provided it's coherent with your other probability assignments. So, if your prior probability of drawing black is 0.5, your prior probability of drawing red must be 0.5. If your prior probability of drawing black is 0.1, your prior probability of drawing red must be 0.9. But either is acceptable, right? You can say 0.1, 0.5, 0.99999, whatever, right? So prior probabilities can come from anywhere. They can be basically anything you like. One interesting feature of subjective Bayesianism then is that there's nothing irrational about maintaining an unjustified belief. So I may assign a very high probability to the proposition that there are unicorns in the Andromeda galaxy. And let's say I do this just because, I feel like it, just because I want to believe that there are unicorns in the universe. I have no evidence for it and no evidence against it. For the Bayesian, there's nothing irrational about, for the subjective Bayesian, there's nothing irrational about continuing to, to hold this probability assignment. Continuing to hold this high prior probability. Rationality comes in, for the subjective Bayesian, in the way that you alter your beliefs, right? You have to update your beliefs by conditionalizing on the evidence. So subjective Bayesianism gives what we might think of as a kind of structural conception of rationality. In a way, it doesn't really matter what you believe. It doesn't matter what the content of your beliefs is, provided that, first of all, your belief system kind of hangs together as a whole. It must be in line with the probability calculus, as per the second tenet of Bayesianism, and provided you change your beliefs in the right way. So you have to change your degrees of beliefs by conditionalization, as with the third tenet of Bayesianism. But that's all, right? That's all that rationality requires. Now, it might seem that this view of rationality leads to an unacceptable degree of just sort of emotion and prejudice in science, right? I mean, we sort of want science to be a mechanism for kind of escaping subjectivity, but subjective Bayesianism seems to embrace subjectivity. Now, so this is obviously a worry, but subjective Bayesians think that this problem can be mitigated because even if two people have very different priors, provided they have access to the same evidence, well, a continued application of Bayesian conditionalization will lead to convergence of belief. So their posteriors will converge, and this is known as washing out of the priors. And it's actually pretty intuitive why this happens. So suppose that Frank, believes H, Vincent does not. So Frank, let's say he assigns 0.9 to the probability of H, Vincent assigns 0.1 to the probability of H. Now, since Frank assigns a high probability to H, he will also assign a high probability to any prediction, E, deduced from H. Vincent, of course, will assign a lower probability to E. Now, remember that Bayes' theorem tells us that the lower the probability of E, the greater its confirmatory power. And what this means is that Frank's value for the probability of H given E will be only slightly higher than his value for the probability of H, whereas Vincent's value for the probability of H given E will be significantly higher than his value for the probability of H. So as the evidence comes in, the posteriors will converge despite radically different priors. Here's just another example from the book Philosophy and Probability by Timothy Childers. Suppose two people disagree on whether a coin will land heads. Frank thinks the coin is biased towards tails. Vincent thinks it's biased towards heads. The black line here shows Frank's prior probability that the coin will land heads next toss. The dotted line shows Vincent's prior probability that the coin will land heads next toss. And, as we toss the coin over and over and over, the probability distributions gradually converge, and actually it's a fair coin. So in the last thing here we have the probability after 200 trials, and they've nearly converged. And, isn't this compatible with how scientists actually behave? After all, they do exhibit a great divergence of opinion in the early stages of inquiry, but as evidence comes in, they gradually form a consensus. Scientists are exposed to large amounts of essentially the same information, the same evidence. Part of the way that science is set up is that all scientists can access the evidence that other scientists have generated. So it's no surprise that even though their priors are very different, their degrees of belief converge. There are, however, issues with this appeal to convergence. So, for one thing, The convergence argument assumes that scientists will agree on whether or not a particular theory entails a particular piece of evidence, but that's often up for debate as well. So just to take an extreme example, let's imagine I accept the hypothesis that God exists, but not only that, I also believe that God is a deceiver, right? God has set things up to make it look like the Earth is billions of years old, when in fact he only created it 5,000 years ago. Well, all of the evidence that you acquire from modern geology can only reinforce my belief. Right? I mean, there's no way that, certainly, assuming that modern that modern sort of science is true, at least broadly true about the age of the Earth, there isn't any way that you're going to get me out of this belief. So in that kind of case, convergence is going to be blocked. And even putting aside problems like this, just as a logical matter, for any amount of evidence you have, it's always going to be possible to choose some set of priors such that the posteriors will still radically differ. And I guess in just more practical terms, we might not gather enough evidence for opinions to converge in the way the Bayesian hopes it will. The Bayesian is ultimately saying belief is going to converge in the long run. But what is the long run? John Maynard Keynes has that famous thing where he says, in the long run, we're all dead. He was objecting to frequentist interpretations of probability, but I think the quote applies here too, right? The Bayesian says, belief is going to converge in the long run, but in the long run, we're all dead. And I think often in science, especially when we're dealing with very sophisticated, abstract theoretical hypotheses, evidence can be quite hard to come by. There's no guarantee that we will gather enough evidence for this convergence to occur. So subjective Bayesianism, that's the main issue there. It's not clear that the convergence argument can really overcome this problem of the fact that subjective Bayesianism seems to make science too subjective. So on the other hand, then, there are objective Bayesians, and objective Bayesians insist that prior probabilities are rationally constrained. So returning to the urn example, where you're told to draw a ball from an urn containing both red and black balls, and no other information is given about the urn, what's the probability that you will draw a black ball? Well, for the objective Bayesian, you certainly can't say that the probability of drawing a black ball is 0.1 and the probability of drawing a red ball is 0.9, because you have no reason whatsoever for thinking that there's a significantly higher probability of drawing red rather than black. The objective Bayesian would say you have to assign 0.5 to both of them. In the absence of any further information, you have to treat them equally. Now, as you start taking balls out the urn, if it turns out that most of them are red, obviously your probability assignment will change. But before you see what's inside the urn, before you're told what's inside the urn, you have no information that you could use to judge one hypothesis or the other to be more probable. And your assignment of prior probabilities must reflect this. So how do we apply this kind of thing to scientific hypotheses? Well, so it seems that the thought is that to assign a prior probability to a hypothesis, we have to list the relevant hypotheses and then distribute probabilities according to what we might call a principle of indifference. So Keynes defined the principle of indifference. He says the principle of indifference is if there is no known reason for predicating of our subject one rather than another of several alternatives, then relatively to such knowledge, the assertion of each of these alternatives have an equal probability. So the thought is that to get the prior probability of some hypothesis H, we list H and all its rivals, and then we give each of them an equal probability. So we just distribute the probability assignment equally over the whole list. And that gives us a unique distribution of prior probabilities, which we can then use as the basis for applying Bayes' theorem. So the prior probability of H in that case is going to be 1 over n, where n is the number of hypotheses on the list. Now, unfortunately, there are several difficulties with this procedure. One serious problem here is how long is the list, right? So it seems like for any phenomenon, there's going to be an infinite number of hypotheses that we could propose to account for it. But if we apply the principle of indifference to an infinite number of rival hypotheses, the prior probabilities of all of them will be 0. 1 divided by infinity is 0. and the probability of 0 can never be increased by new evidence. On the other hand, if we take a finite list, so we're not including every possible hypothesis, what criterion should be used to determine what ought to be included on the list? So that's a big issue. A very similar problem is that different descriptions of the same situation will yield different prior probabilities by applying the principle of indifference. So Bas van Frassen has a really nice example that illustrates this problem. Suppose there's a factory that makes cubes, and you have only two pieces of information about the factory's cubes. First, all the cubes are exactly the same shape and size, and second, the side length of these cubes is somewhere between 0 and 2 meters. Now take the hypothesis. The side length of the cubes from the cube factory is between 0 and 1 meters. What probability do we assign to this? Well, it seems the principle of indifference would tell us that we should, assign the same probability to this as to the hypothesis that the side length is somewhere between 1 and 2 meters. Right? We have no reason to prefer one hypothesis to the other. So we assign it probability 0.5. Okay, but now consider this variation. There's a factory that makes cubes, and again, you're given two pieces of information about these cubes. All the cubes made by the factory are the same shape and size, and the surface area of each face of the cubes is somewhere between 0 and 4 square meters. Now, the hypothesis. The face area of the cubes from the cube factory is somewhere between 0 and 1 square meters. Well, applying the principle of indifference in this case, it looks like we should give equal probability to 4 hypotheses, right? The hypothesis that the face area is between 0 and 1 square meters, between 1 and 2 square meters, 2 and 3 square meters, 3 and 4 square meters. So we have a probability of 0.25. The problem here is that I've just described exactly the same situation, exactly the same hypotheses in two different ways. So if the side length is 1 meter, the face area will be 1 square meter. But if the side length is 2 meters, the face area will be 4 square meters. So, in fact, these two hypotheses that we've just considered are exactly the same hypothesis. It makes no sense to assign a different prior probability to each of them. It's inconsistent to assign 0.5 to the first and 0.25 to the second. So the principle of indifference gives different probability assignments depending on how you describe the problem. If you describe the cubes in terms of side length, you get a different way of partitioning the hypotheses than if you describe it in terms of face area, and that's a different way again than if you were to describe it in terms of volume. So of course an objective Bayesian wouldn't necessarily have to use the principle of indifference to determine the prior probabilities, but this I think gives a flavour of some of the difficulties facing objective Bayesians. So I think it's fair to say that most Bayesians tend to be subjectivists. They tend to think that there are no constraints on prior probability beyond the probability axioms, or at least there are very few constraints on prior probabilities. But anyway, I think that that's enough for today. As I said, we've really only scratched the surface of Bayesianism here, but I hope that gives a flavour for what the fundamental ideas of Bayesianism are. And in the next video, we'll consider some objections. So thanks for watching. Goodbye.